Picture the phrase light year for a moment. It sounds like time, doesn't it? A year of light, something you measure with a clock. But that is a trick your ears play on you. A light year is not time at all. It is a distance, and it is one of the largest distances your mind will ever try to hold. So let me set a simple challenge. Take the fastest machine humanity has ever built, point it at a single light year of empty space, then ask one honest question. How long would the crossing take? The answer is not minutes, it is not years, it is thousands of years, sometimes tens of thousands of years. And that is with the engine already at full speed, ignoring the time to speed up or slow down. Here is the part that surprises most people. The obstacle is not a weak engine. We could build a bigger one. The wall we hit is written into the nature of space itself, into time, into speed. These are limits you cannot argue with and cannot bribe your way past. So let me show you just how thick that wall really is. Start with something you already know. A passenger airplane cruises at 800 kilometers per hour. That is faster than a good maglev train. It feels fast when you look out the window. Now aim that plane at 1 light year and let it fly without stopping. How long? 1 million years. During that flight, thousands of human generations would be born and would die. Continents would drift into new shapes, and the plane itself would rust, crack, and crumble into dust long before arrival. Let me slow it down further to make it truly human. Picture a car on an open road at 100 kilometers per hour. No stops, no sleep, no refueling. It simply drives forever. To cover 1 light year, that car would need 10,800,000 years. Try to feel that number. In that span, apes evolved into humans. Those humans built cities. They invented the internet. They flew into space. All of it, from the first stone tool onward, fits inside that single drive, and here is the detail that seals it. That car's journey equals 23.5 million trips around the equator of the Earth, round the whole planet, again and again, over 23 million times. That is 1 light year measured in laps of home. Now let me flip your sense of scale using light itself. The moon sits 384,000 kilometers away. The Apollo rocket took 3 days to reach it. That felt like a heroic voyage. Yet light crosses that same gap in about 1 second. Blink once and the light has already arrived. You cannot even blink twice in time. Push out to Mars. On average, it lies 60 million kilometers from us. A real spacecraft needs roughly 7 months to make that trip. 7 long months of drifting through the dark. And light? Light crosses to Mars in about 3 minutes, just enough time to brew a tea bag. That is the gulf between how we move and how light moves. So hold this in your head. 1 light year equals 525,000 minutes of pure light travel, not our slow travel, light's travel. The Earth-Moon distance fits into 1 light year 24 million times over. That's like laying a single hair beside Mount Everest. And the distance from Earth to the Sun, 1 astronomical unit, fits inside a light year 63,000 times. The numbers stop being numbers. They become a kind of silence. We've measured the wall with cars and planes and beams of light. Now let's throw our very best machine at it. In 1977, we launched Voyager 1. Picture an iron robot about the size of a small car. It carries instruments, a radio transmitter, and a dish antenna. It is the farthest human-made object in existence. Nothing we have ever built has traveled deeper into the dark. And Voyager 1 is fast. It moves at 17 kilometers per second. That's over 60,000 kilometers per hour. Every single second it covers 17,000 meters, the width of a large city, in 1 heartbeat. For nearly 50 years it has raced outward. It has already left the heliosphere, the sun's protective bubble, and now drifts through true interstellar space. So after 50 years of that blistering pace, how far has it gone toward 1 light year? 1,000th. A single thousandth of the way. To cross a full light year, Voyager 1 would need about 18,000 years. Feel that number against history. 18,000 years ago, the Earth was gripped by an ice age. People sheltered in caves, they hunted mammoths, they huddled beside fires for warmth. Now imagine the probe leaving back then. Over its flight, the Egyptian pyramids would rise. Ancient Rome would climb to greatness and then collapse. The Middle Ages would come and go, all of modern history would unfold, and only then would it arrive. So we need something faster, and we have it. In 2018, we launched the Parker probe to study the sun. The sun's enormous mass pulls hard on everything nearby that gravity became an engine. It flung the probe to a record speed. By late 2024, the Parker probe reached about 630,000 kilometers per hour. That's roughly 175 kilometers every second. Let that land. At that speed, you could fly from Moscow to St. Petersburg in 4 seconds. 4 seconds between two cities. The Parker probe is the fastest human-made object ever created. Nothing we've built moves quicker. Surely this cracks the wall? Point it at 1 light year and check. The Parker probe would still need about 1,700 years, 17 centuries, at record speed. 1,700 years ago, Roman legionnaires still marched across the earth. No cars, no electricity, no printed books. That is the era you depart from, to only just arrive today. And this exposes a brutal human problem. An average person lives about 80 years. Imagine a 20-year-old cosmonaut launched at Parker's speed. He would grow old in that cabin. He would die in that cabin, and he would never reach the destination, not close. So you couldn't send one person. You'd need a flying city, a vessel where people are born, learn, work, grow old and die, across dozens of generations. And even that dream breaks on a simpler truth. No technology runs flawlessly for 1,700 years. Metal rusts, wires dry and crack. Batteries lose their charge. The machine would die long before the mission ended. So the answer is obvious, right? Build a bigger engine, add more fuel. Except that path is a trap, and a scientist proved it long ago. His name was Konstantin Tsiolkovsky, and he wrote the rocket equation. It reveals a cruel fact. On a rocket, the fuel weighs far more than the ship's body and everyone inside it combined. On a modern rocket, 90% of the launch mass is liquid fuel and oxygen. Only 10% is the metal, the engines, the cabin, and the payload. Here's why that spirals out of control. To lift the first ton of fuel upward, you must first burn 2 more tons of fuel. Fuel to carry fuel to carry fuel. So doubling a ship's speed doesn't double the fuel. It multiplies it by tens, even hundreds of times. The cost explodes. Now push that math to our goal. To cross 1 light year in 100 years with an ordinary rocket, the fuel tank would need to weigh more than the entire Earth, more than all its oceans and mountains. That is not expensive. That is physically impossible. You cannot build a fuel tank heavier than the planet you launch from. And even if you somehow could, space would fight back. Because there's a second danger, and it hides in the emptiness itself. Space only looks empty. In truth, it is scattered with countless grains, specks of dust, and tiny rocks. At normal speeds, they mean nothing. But at high speed, every one of them becomes a bullet. Consider a single grain weighing 1 gram. Now hurl your ship past it at 30,000 kilometers per second, 10% of light speed. That harmless grain now carries the energy of a powerful explosion. It would punch straight through titanium armor and tear the ship apart. So armor up, you might say, but look at the numbers. A shield of iron and concrete thick enough to survive would need to be as tall as a multi-story building, and that shield has mass. Mass demands more fuel. More fuel demands even more fuel. You're right back inside Tsiolkovsky's vicious circle. There is no escape by adding weight. So one truth becomes clear. Ordinary gasoline or kerosene engines will never carry us across 1 light year. The old way is finished. The real question is this: can a completely new idea slip around physics instead of fighting it head-on? Some engineers think yes. Consider Project Breakthrough Starshot. Their idea flips everything. Don't launch a giant crewed ship. Launch a tiny electronic chip. The chip is the size of a postage stamp. It weighs only 2 grams. To that chip, they attach a thin, reflecting sail about the size of a 4-person tourist tent. Then comes the engine, and it stays on the ground. On Earth, you build a vast battery of thousands of powerful lasers. You aim them all at one point on that sail. Here's the key. Laser light has no mass, yet it can push objects. It shoves the light sail forward. Within minutes, the lasers accelerate the tiny probe to 60,000 kilometers per second. That's 20% of the speed of light. At that speed, the chip crosses 1 light year in only 5 years. 5 years, not 18,000. The wall suddenly looks thin, but there are 2 hard catches. First, no human can ride a postage stamp. there's no room for a body, let alone a life. Second, the probe has no brakes. The ground laser can only push, never pull. So the chip screams past its target and continues on into the darkness forever. So we can send a machine fast, but never stop it, and never send ourselves. To send a living human, you'd need something far grander. A ship with a powerful nuclear engine, accelerated close to light speed, 300,000 kilometers per second. And at that extreme, something strange and beautiful happens to time. Albert Einstein proved it. At enormous speeds, time slows down around you. Let me show you with two twin brothers. Both are exactly 20 years old. One stays home on Earth. The other flies at near light speed across 1 light year and back. Inside that ship, everything runs slow. The cosmonaut's clock ticks slower. His heart beats slower. His very cells age slower. His clock hand makes 1 full turn while a whole month passes back on Earth. Near maximum speed, the entire 1 light year trip could feel like just weeks or a couple of months to him. He steps out fresh and young, but here is the cruel twist. Time dilation works only for the one inside the fast ship. On Earth, time runs at its normal pace. While the cosmonaut lives through a couple of months, more than a full year passes on Earth. And once you count the time to speed up and slow down, decades pass at home. A round trip might cost the traveler under a year, yet he returns to a changed world. His twin brother is now an old, gray-haired man, or already gone. His friends have aged. His cities are transformed. So physics does allow a human to survive a 1 light-year flight. Time dilation is real, but the price is total. You lose every connection to your past. It is a one-way ticket, not into another place, but into another time. If speed itself is such a trap, maybe the trick is to cheat distance. Two theoretical ideas try exactly that, mathematical bypasses written only as formulas on paper. The first is the Alcubierre drive. Instead of accelerating the ship, a giant installation reshapes space. It compresses space in front of the ship and expands it behind. Picture standing on a carpet. Rather than walking forward, you grab the far end of the carpet and pull it toward your feet. The ship never truly moves. It sits still inside a bubble, while space itself contracts around it. In theory, this could cross 1 light year in just a few days and never break the light speed limit at all. The second idea is the wormhole. Imagine a flat sheet of paper. Earth sits on one edge, your target on the far edge. Now fold the paper so the two edges touch. The distance between them shrinks to 0. You simply step through and you're there instantly. Both ideas are dazzling. Both exist only on paper. To compress space or to fold the universe, you need something called negative energy. And to create a single one of these bubbles, you'd have to burn mass the size of the giant planet Jupiter. We have no technology for that, no source of energy remotely close. So step all the way back and see the full picture. The observable universe stretches 93 billion light-years across. It holds trillions of galaxies. Against that, 1 light-year is thinner than a hair. It is nothing, a rounding error. And yet for us, with the tools in our hands today, that same 1 light-year stands like an invisible wall of reinforced concrete. But walls have been broken before. Right now, in real laboratories, engineers are building the first true laser installations to launch those microprobes, not fantasy, hardware. In a couple of dozen years, humanity may send its first craft toward the 1 light-year mark and receive real photographs back from deep space. Remember what we already did. We learned to cross oceans that once seemed endless. We learned to fly through air that once held only birds. We reached orbit and looked back at our whole world at once. Crossing 1 light-year is simply the next step, the one not yet taken. And here is the quiet payoff hidden in all these numbers. That 2-gram chip, no bigger than a stamp, could ride a beam of light across a distance our fastest rocket would need 18,000 years to touch, and it could do it in just 5 years. The wall is real, but the ladder against it is already being built.
Let me share something fascinating right at the start. We are extraordinarily lucky to exist in this particular sliver of cosmic time. Stars are still burning out there, billions of them, and that simple fact makes us almost cosmically privileged. Because when you zoom out and look at the full sweep of universal history, The era of starlight turns out to be a brief, shining exception in an otherwise endless darkness. Almost everything that will ever happen to this universe will happen in the cold and the black, long after the last sun has gone quiet. So what does the death of the universe actually look like? That's what I've spent decades trying to understand, and what I want to walk you through right now. Settle in, because this is going to be quite a ride. Here's where we start. Roughly 100 trillion years from now, the final star will exhaust the last of its hydrogen fuel. It'll collapse inward, shrinking into a white dwarf, a dense, dimly glowing ember that will slowly bleed away its remaining warmth into the void. Eventually, it too will go dark, becoming what astronomers call a black dwarf. At that point, the stellar era ends. And just to give you a sense of scale, those 100 trillion years represent roughly 10,000 times the current age of the universe. Starlight, in other words, has a good long run ahead of it. But in the grand accounting of cosmic time, even that run is just an opening act. You know what's interesting? Even after every single star is extinguished, the universe won't have experienced anything close to true old age. The epochs that follow will make the stellar era look like a Tuesday morning. The universe will spend the overwhelming majority of its existence, essentially all of it, in a state of accelerating darkness, inching toward maximum entropy, toward what physicists call heat death. But don't mistake that slow march for uneventfulness. There are still mechanisms at work, processes that will gradually transform what's left into something far less interesting in the technical thermodynamic sense. The universe cools, energy disperses, entropy climbs. Now, could civilization survive all this? Possibly. A sufficiently advanced civilization might learn to harness the very processes of cosmic decay, riding them like a wave rather than being crushed by them. Life and structure can persist as long as the universe remains out of perfect equilibrium. That equilibrium, heat death, is the finish line. Our goal today is to figure out two things. How long does it take to reach that finish line, and what are the specific milestones along the way? Scientists and science fiction writers have sketched out all kinds of endpoints for our civilization. Earth destroyed by asteroid impact. The sun expanding into a red giant, swallowing our planet. The Andromeda Galaxy, currently about 2.5 million light-years away, slamming into the Milky Way. Eventually, that last scenario plays out. Our galaxy merges with Andromeda, and the resulting structure is composed almost entirely of stellar corpses, neutron stars, black holes left behind by massive stars, and white dwarfs shed by smaller ones. Those white dwarfs, as I mentioned, will eventually cool into black dwarfs. That cooling process takes a few billion years. Fast compared to how long the stars themselves burn, but still an immense stretch of time on any human scale. And all the while, a serious question looms over whatever remains of life. Where do you get your energy? Civilizations that survive into the red dwarf era, the long, slow twilight dominated by the universe's smallest, coolest stars, will have to fundamentally rethink their relationship with energy. Their connection to the broader cosmos will be severed long before that era ends. I've spent decades studying this, and one of the most striking things about the far future is what expansion does to the observable universe. The accelerating expansion of space means that galaxies are being pushed apart faster and faster. Eventually, galaxies beyond our local group will recede past what's called the cosmic event horizon, a boundary beyond which their light can never reach us, no matter how long we wait. By the time the red dwarf era kicks into full gear, even the cosmic microwave background radiation, the afterglow of the Big Bang itself, will have red-shifted into undetectability. Future civilizations will look out and see only their own galaxy. Every piece of evidence that a Big Bang ever happened will have vanished from view. All right, the stellar era is over. What's next? We enter what I call the degenerate era, an age of decay. What's left in the universe at this point? Compact, ultra-dense objects, neutron stars, black holes, and those black dwarfs, the cooled-down remnants of former white dwarfs. From a quantum mechanical standpoint, these objects are packed to their limits. Every available quantum state is filled. The only way to compress them further is to cross the threshold into black hole territory. Interestingly, many of these black dwarfs may still have planetary systems orbiting them, remnants from their stellar youth. Imagining civilizations clinging to existence on pitch-black worlds around cold stellar corpses stretches the imagination, but it's not ruled out by physics. However, even those worlds are living on borrowed time. Here's what brings them down: gravitational encounters. As stellar remnants drift through the galaxy, they occasionally pass close to one another. These near misses tug at the planets in orbit, slowly ejecting them or pulling them in. Over a time scale of roughly 1,000 trillion years, that's 10 to the 15th power, essentially every planetary system in every galaxy will be disrupted. Planets flung into the void, or spiraling into the dense stellar remnants they once called home. And then there's the ultimate fate of the galaxies themselves. Gravitational dynamics within the merged Milky Way Andromeda system and in galaxies everywhere will continue operating even after starlight is gone. The lighter remnants, mostly black dwarfs plus frozen planets and asteroids, will gradually be flung out of the galaxy entirely. The heavier bodies, neutron stars, black holes, will sink toward the center. According to calculations by Freeman Dyson, somewhere between 90 and 99% of all stellar remnants in our galaxy will be ejected over approximately 10 to the 18th power years. By that point, the universe is 1,000,000 times older than it was when the last star died. Give it another factor of 10, and whatever's left in the galactic core will either collide with something or be swallowed into a supermassive black hole sitting at the center. And that brings us to one of the biggest unresolved questions in physics. Do protons decay? Let me explain why that matters. Protons are the most stable composite particles we know of. According to the standard model of particle physics, they should last forever. But certain theoretical extensions of the standard model, grand unified theories, predict that protons can eventually decay, converting into positrons, neutrinos, and gamma-ray photons. We've never observed this happening. Enormous underground detectors filled with water have been watching for decades, and so far nothing. That non-observation tells us that if protons do decay, their half-life must be at least 10 to the 34th power years. If proton decay is real, then somewhere between 10 to the 39th and 10 to the 40th power years from now, every proton in the observable universe will be gone. Planets, black dwarfs, cosmic dust, all of it dissolves into a thin soup of photons, leptons, and black holes. Welcome, ladies and gentlemen, to the black hole era. Now, black holes are fascinating objects, and not just because of their gravitational grip. They also radiate. Stephen Hawking showed that quantum mechanical effects cause black holes to slowly emit particles, mostly low-energy radiation, gradually losing mass over time. This process, known as Hawking radiation, is almost incomprehensibly slow for large black holes. A stellar mass black hole of about 10 solar masses needs roughly 10 to the 67th power years to fully evaporate. And the giants, the supermassive black holes that once anchored entire galaxies, potentially containing hundreds of trillions of solar masses, could persist for up to 10 to the 106th power years. That's 1,000,000 Google years. It's a number that doesn't fit inside a human brain, and I've tried. During the black hole era, a sufficiently advanced civilization could theoretically still extract usable energy. Black holes can function as exotic engines, through Hawking radiation at minimum, or through more elaborate mechanisms like the Penrose process, which extracts rotational energy from spinning black holes. If life finds a way to tap those sources, it buys itself an almost unimaginable extension of time. What about dark matter? By this point, it's almost certainly gone too, either annihilated through particle collisions or captured by dense stellar remnants earlier in the degenerate era and eventually swept up into black holes. Then comes the end of the black hole era itself. One by one, the last black holes flicker out in bursts of gamma radiation, brief, brilliant flashes that will light up the universe for the first time in countless eons. After those final explosions, what remains is an expanding, thinning fog of elementary particles and photons. No gravity to pull them together, no energy gradients to exploit. Just an ever more dilute mist spreading across an ever-expanding space. That's heat death. That's the terminus. But, and here's where I want to backtrack, I've been assuming protons do decay. What if they don't? This changes the timeline dramatically, though not the destination. Without proton decay, the denser stellar remnants remain intact far longer. But quantum mechanics doesn't let anything stay truly stable given enough time. A process called quantum tunneling, which lets particles cross energy barriers they classically shouldn't be able to cross, will slowly transform matter into its lowest possible energy state. Think of a marble rolling toward a hill it doesn't have enough energy to climb. Classical physics says it stops at the base. Quantum mechanics says there's a small but non-zero probability it passes through the hill as if it weren't there. Applied to matter on cosmic timescales, quantum tunneling means that elements lighter than iron will gradually fuse into heavier ones, while elements heavier than iron will decay toward it. Iron represents the bottom of the nuclear energy valley, the most stable nuclear configuration. So the end state, for all remaining matter, is perfect iron spheres. Former planets, former asteroids, former black dwarfs, all converted into giant iron balls over approximately 10 to the 1,500th power years. Even those iron spheres won't last forever. Quantum tunneling will also cause matter to migrate from the surface toward the core, gradually pushing these objects toward neutron star-like densities. That process takes on the order of 10 to the power of 10 to the 76th years. But here's a possible shortcut. If tiny black holes are physically possible, and Freeman Dyson noted that the minimum black hole mass might be the Planck mass, about 20 micrograms, then quantum tunneling could cause small nuclei within larger bodies to collapse into microscopic black holes, which then consume the surrounding matter. In that scenario, everything larger than a dust grain collapses into a black hole within 10 to the power of 10 to the 26th years, and then those black holes evaporate via Hawking radiation on the usual schedule. So whether protons decay or not, the destination is the same, a gradually dispersing haze of particles expanding through an accelerating universe incapable of supporting any structure or process that could harness energy. The timeline differs. 1,000,000 Google years if protons decay, something far more extreme if they don't, but the endpoint is identical, heat death. Now I'd be doing you a disservice if I didn't mention a few alternatives, not scientific predictions, but genuine physical possibilities that some researchers find worth considering. First, dark energy might not be constant. If its strength grows over time, it could eventually become powerful enough to tear apart galaxies, then solar systems, then planets, then atoms themselves, a scenario called the Big Rip, a violent counterpart to the slow fade of heat death. Second, quantum fluctuations in a sufficiently old universe might spontaneously nucleate entirely new universes in small pockets of space, each beginning its own Big Bang. Third, if gravity somehow overcomes dark energy in isolated regions, those regions could collapse back into singularities and re-expand, essentially running local versions of the Big Bang with lower initial energy, a kind of cosmic recycling. These aren't hypotheses in the strict scientific sense, they can't be tested, but they're not mere fantasy either. They emerge from legitimate physical frameworks. I leave them to the theorists and science fiction writers who are equally qualified to explore them. What we can say with confidence is this: the death of the universe will arrive somewhere between 1,000,000 Google years and 10 to the power of 10 to the 50th years from now, numbers so large they're essentially meaningless to intuition, but not to mathematics. And the physics that governs those final eons, we've actually made serious progress in describing. We exist in the bright, warm, star-filled opening pages of a story that will run for an almost incomprehensible length of time. Most of that story will be dark and cold and quiet. But here we are in the lucky chapter, asking questions about the ending. I've spent my entire career on questions like this one, and I still find it breathtaking. The universe will die, but understanding how it dies tells us something profound about what it is right now and what it means that we're here to watch. Here's a question nobody is asking out loud. What if the Artemis program was never really about putting boots on the moon? What if the lunar landings, the rockets, the astronauts, the whole spectacular show are just the opening act for something far bigger? Let me share something fascinating with you. In March 2026, NASA unveiled a plan so detailed, so ambitious, and frankly so unexpected that even I had to sit down and read it twice. And I've spent decades studying this agency. What they're building isn't a flag-planting moment, they're building a city. When NASA Administrator Jared Isaacman stepped up to the podium at agency headquarters in Washington, D.C., there was a single word lit up on the projection screen behind him: ignition. Not exploration, not discovery. Ignition, that choice of word told you everything about the shift in attitude. Gone is the cautious, committee-driven NASA of the past 20 years. What replaced it is an agency that has looked at decades of wasted taxpayer money, we're talking billions, and decided that getting comfortable with failure is no longer an option. You know what's interesting? The urgency here has almost nothing to do with science. It's geopolitical. China has its own lunar program, and unlike the space race of the 1960s, which was essentially a televised propaganda competition, this one comes with real estate attached. Whoever establishes a permanent functioning presence on the moon first will have leverage over the most valuable territory beyond Earth. Isaacman made no secret of this. The message was simple. The moon is not up for grabs anymore. America is going to stay there. Now, here's where things get genuinely interesting and a little counterintuitive. The first major structural change to the program is that Artemis 3 will not land on the moon. I know. Hear me out. Under the previous plan, the program was set to leap directly from Artemis 2, a crewed orbital test flight of the Orion capsule, straight to a full lunar landing using a separate vehicle that had never been crewed before. Not tested with humans, not proven in deep space conditions. Just hope for the best and go. That was the plan, and unsurprisingly, the launch date kept sliding forward year after year, like a can being kicked down an endless road. The revised approach is far smarter. Artemis 3 is now a dress rehearsal conducted in low Earth orbit. The Orion spacecraft will rendezvous and dock with the lunar lander, the crew will board the lander, and every critical system, life support, propulsion, communications, the new lunar EVA suits, gets a real-world workout at an altitude where rescue is still theoretically possible. I've spent decades studying this industry, and let me tell you, this is how serious engineering gets done. You don't take 3 people to the moon in a vehicle that has never had a human inside it. And there's another twist nobody saw coming. SpaceX no longer has a monopoly on the moonshot. Blue Origin and their Blue Moon lander are back in the running alongside SpaceX's Starship variant. Isaacman put it bluntly, winning a contract in 2022 doesn't guarantee you a seat at the table in 2027. What matters is who actually delivers a working vehicle on time. The first company to get their lander ready wins the honor of carrying American astronauts to the lunar surface. That's not a subtle hint. That's a fire lit under both programs simultaneously. So where does this leave the schedule? Artemis 3 is now targeting 2027 for its low Earth orbit rehearsal. After that, whichever lander passes the test goes directly into an uncrewed lunar landing, a final shakedown, and then pivots immediately into Artemis 4, set for early 2028. That mission brings Americans back to the lunar surface for the first time in over half a century, touching down somewhere in the South Pole region. And then, before 2028 is even over, Artemis 5 follows. 2 lunar landings in a single calendar year. That's not a typo. For reference, Apollo 11 landed on July 20th, 1969. Apollo 12 followed on November 19th, 1969. That's 122 days between moon landings. NASA used to do this routinely. The goal now is to re-establish that rhythm. A crewed lunar mission approximately every 6 months, indefinitely. That cadence isn't just about optics. It's the only way to build and sustain what comes next. Speaking of what comes next, let me share something that surprised even me. The Lunar Gateway Space Station, which was the centerpiece of NASA's orbital infrastructure plan for years, has been canceled as a standalone project. Done. The idea of assembling a space station in lunar orbit first and using it as a staging point for surface missions has been shelved. But here's the good news. All the hardware that's already been built for Gateway doesn't get thrown in a landfill. Every module, every component, every system gets redesigned and repurposed as part of the surface base itself. A $20 billion budget has been committed to building that base over 7 years, and the construction plan is broken into 3 distinct phases. Phase 1 runs from 2026 through 2028. 25 missions are planned during this window, with 21 of them targeting the lunar surface. Only 2 will carry crews, but the other 19 are anything but trivial. This phase is about figuring out how to survive on the moon before committing people to living there. One of the biggest problems to crack is power. The lunar day-night cycle lasts roughly 29.5 Earth days. 2 weeks of blazing sunlight, then 2 weeks of total darkness during which surface temperatures plunge to around minus 280 degrees Fahrenheit. That kind of cold doesn't just drain batteries, it destroys electronics permanently. NASA's solution involves radioisotope thermal generators, devices that use the natural heat released by decaying radioactive materials like plutonium-238 to keep hardware above the survival threshold. No moving parts, no fuel required, just steady, reliable warmth in the dark. Phase 1 also introduces one of the most unusual vehicles in NASA history, rocket-propelled exploration drones they're calling Moonfall. Think of the Ingenuity helicopter that flew on Mars. Now strip out the rotors and replace them with small rocket thrusters, because there's no atmosphere on the moon to generate lift. Each Moonfall drone can execute a hop of up to 50 miles and stay airborne for about 150 seconds. They'll be sent into places too dangerous or too steep for wheeled vehicles, the rims of deep craters, the tops of ridgelines, permanently shadowed zones. You know what's interesting? Some of the most scientifically valuable spots on the moon are also the most geologically treacherous. These drones solve that problem. Also launching in 2027, the Viper rover. This golf cart-sized robot has been sitting in storage, fully assembled and tested, waiting for a ride. It's finally getting one, courtesy of a Blue Origin lander. VIPER's mission is lunar prospecting, systematically mapping the South Pole for confirmed deposits of water ice and useful volatiles like hydrogen, oxygen, and rare earth elements. Those resources aren't just scientifically interesting, they are the raw material for everything that comes later. Joining Viper on the surface will be 2 lunar terrain vehicles, 1 crewed and 1 autonomous, each with a range of about 5.5 miles. These aren't just exploration tools, they're workhorses, built for moving equipment and preparing ground for construction. Overhead, a new constellation of lunar communications and navigation satellites will provide continuous, uninterrupted data relay between any point on the lunar surface and Earth. Bandwidth is projected at 500 megabytes per second, and every rover, every drone, every vehicle will carry high-definition cameras streaming live to anyone on Earth who wants to watch. NASA has mandated this. The moon is going to be live television all day, every day. I've spent decades watching NASA manage its public image, and this is by far the most aggressive transparency commitment they've ever made. Phase 2 covers 2029 through 2032, with 27 launches and 24 landings planned. This is where infrastructure stops being experimental and starts being permanent. 6 additional rovers arrive, not just for exploration, but for excavation. These machines are designed to move rock, grade terrain, dig trenches for buried power lines, and level construction pads. Phase 2 also delivers the first pressurized mobile habitat, a 33,000-pound rolling laboratory developed jointly by the Japan Aerospace Exploration Agency and Toyota. Crew members inside can work in regular clothes at comfortable temperatures, traveling at roughly 2 miles per hour for days at a stretch. The vehicle is rated for a decade of operation and can function for up to 150 consecutive hours in total darkness. Power generation scales up dramatically in Phase 2. Solar arrays mounted on tall poles will feed large battery banks for daytime energy storage, and supplementing that, nuclear fission reactors. Not the small radioisotope heaters from Phase 1, but full fission systems generating hundreds of watts of continuous electrical power capable of running multiple systems at once. By 2032, the infrastructure exists to keep humans alive on the Moon indefinitely. Phase 3 is where they actually move in. From 2033 onward, the Artemis moon base will support rotating crews of 4 people for 28-day stays. Multiple connected habitat modules, pressurized and powered by dedicated fission generators, will form what amounts to a surface-based space station. Around 17,600 pounds of consumables, food, water, breathable air, will need to arrive every month to sustain operations. That's a massive logistics pipeline, and building it is one of the program's central engineering challenges. Outside the habitat, Phase 3 is when in-situ resource utilization begins in earnest. Water ice extracted from permanently shadowed craters gets split by electrolysis into hydrogen for rocket fuel and oxygen for breathing. Lunar regolith, the fine dust and rock that covers the surface, gets processed through 3D printing systems that melt it into a material similar to concrete, enabling the construction of genuinely permanent structures. Not inflatable modules, not temporary outposts, structures built from the Moon itself. Now let me give you the honest version of what this is really about, because NASA said it themselves. The true objective of the Artemis program, the thing that justifies all of it, isn't the base, it isn't the science, it isn't even the geopolitical advantage, though that matters enormously. The real goal is to show the next generation of engineers and scientists something they haven't seen in their lifetimes, an American space program that does what it says it's going to do. NASA acknowledges that what they're attempting is just short of impossible, but they're doing it because impossible is exactly the bar you have to set if you want to produce people capable of doing the truly unprecedented things that come after. I've spent decades studying this. I've watched NASA make promises and miss them, overpromise and underdeliver, and gradually lose the cultural authority it once had. What I'm seeing in 2026 looks different. The schedule is specific. The budget exists. The competition is real. And for the first time in a long time, the plan has a spine. Whether it holds, whether the rockets fly on time, whether the landers work, whether the base actually gets built. That's still an open question, but the blueprint is finally on the table, and it's one worth taking seriously.
2, 1, 0, all engine running.
July 20th, 1969. 600 million people are glued to their television sets, the largest audience in human history. Walter Cronkite can barely get the words out. A crackly voice from 239,000 miles away says the Eagle has landed, and grown men in mission control burst into tears. Neil Armstrong climbs down that ladder, steps onto the surface and says the line that every person alive will remember for the rest of their lives. The world erupts. America wins the space race. Case closed. History made. Go home. Except, here's what nobody told you. That moment everyone remembers? It was almost scientifically useless. NASA was so obsessed with getting there first that the actual research was barely an afterthought. The real discoveries, the ones that changed everything we know about the moon, about Earth, about where we all came from, those happened on the missions nobody talks about, the ones that came after. Let me share something fascinating about what happened just 4 months later, November 14th, 1969. Another Saturn V sits on the pad at Cape Canaveral, fueled and ready. The crowds are thinner this time. The novelty has faded, but President Nixon himself is in the viewing area. Then the weather turns ugly. Rain sweeps in. Lightning splits the sky and strikes the rocket. Not once, twice. Alarm lights flood the control panels. For a few terrifying seconds, Apollo 12 teeters on the edge of becoming NASA's worst disaster. Inside the capsule, Commander Pete Conrad is already running abort procedures in his head. And then, through the radio, comes a voice from Mission Control. Try SCE to AUX. To almost everyone listening, that might as well have been spoken in a foreign language, but astronaut Alan Bean recognized it instantly. The signal conditioning equipment, basically the black box that translates the ship's electrical data into readable information for the crew, had been shorted out by the lightning strike, turning all the instrument readings into gibberish. Switching to AUX connected the backup power supply. Think of it as hitting Control-Alt-Delete at 30,000 feet. The gauges flickered back to life. Apollo 12 was going to the moon after all, and it was going there with a very specific purpose. Forget the glory of being first. That chapter was closed. This time NASA wanted to prove something more operationally critical, that they could land a spacecraft not just anywhere on the lunar surface, but exactly where they intended. Within 3 days, the lunar module touched down with extraordinary precision, no more than 600 feet from Surveyor 3, an unmanned probe that had been sitting on the moon for over 2 years. Conrad and Bean walked over, removed several components, and brought them home. Back in the lab, scientists found that certain materials had survived years of vacuum, intense radiation, and temperature swings that would destroy most Earth-based equipment. For the first time, there was hard evidence that technology, and possibly even microorganisms, could endure long-duration spaceflight. You know what's interesting? The crew also deployed NASA's first ALSEP station, a suite of scientific instruments that included seismometers designed to listen to the moon's interior for years. What they heard was astonishing. When NASA deliberately crashed spent rocket stages into the surface to test the seismometers, the moon didn't just shake. It rang like a bell, with vibrations echoing for nearly an hour. On Earth, seismic energy dissipates within minutes. The lunar readings told a completely different story. A world that is bone-dry, heavily fractured, and structured quite unlike our own. With a distinct crust, mantle, and an unusually small core. While the public had already moved on, Apollo 12 gave the scientific community something to work with for decades. The precision landing capability it demonstrated made every subsequent mission possible. Without that proof of concept, the targeted geological sampling that defined Apollos 15 through 17 could never have happened. Now, I've spent decades studying this period, and nothing in the Apollo story is more remarkable than what came next. April 11th, 1970, Apollo 13 lifts off toward the Fra Mauro Highlands, crewed by Jim Lovell, Jack Swigert, and Fred Hayes. The first 2 days unfold without incident. Then, more than 200,000 miles from Earth, words crackle across the radio that will be repeated forever. An oxygen tank in the service module has exploded. Debris punches through a second tank. The fuel cells that power the command module begin to fail. Electricity drains. Oxygen disappears. In the span of a single minute, a routine lunar landing becomes a fight for survival. The only lifeboat available is the lunar module Aquarius, designed to carry 2 people for a short surface excursion, now pressed into service as a 3-person survival pod for a 4-day journey home. Cabin temperatures plunged toward freezing. Condensation crept across the walls. Food went cold. Fred Hayes developed a kidney infection, and then carbon dioxide levels began climbing toward lethal concentrations, while the square CO2 scrubber canisters from the command module were physically incompatible with the round ports in the lunar module. The engineering team back in Houston improvised a fix using nothing but materials already aboard the spacecraft: duct tape, plastic bags, cardboard from a flight manual cover. They talked the crew through building it step by step. That cobbled-together contraption pulled poison out of the air and kept 3 men alive. Every course correction had to be calculated by hand on slide rules and radioed up. Even the return trajectory had to be eyeballed, literally aligning Earth and Sun in the window to set the heading. After 6 days of sustained improvised problem-solving, Apollo 13 splashed down safely in the Pacific. No moon rocks, no experiments, but something arguably more valuable: a complete, documented proof of what human ingenuity can accomplish when the alternative is unthinkable. The flight that followed was tasked with recovering the program's credibility. January 31st, 1971. Apollo 14 heads back to Fra Mauro, the very site Apollo 13 had been forced to abandon. At the helm is Alan Shepard, the first American to fly in space, a full decade earlier, now finally getting his shot at the moon. Almost immediately, things go sideways. During the approach phase, the command module repeatedly fails to dock with the lunar module. Without a hard connection, Shepard and Edgar Mitchell will never reach the surface. Engineers cycle through every procedure in the book. Nothing works. Finally, Shepard takes manual control and rams the 2 vehicles together hard enough to force the latches to engage. Crisis averted. Barely. On February 5th, the 2 men step onto the highlands that had eluded the previous crew. Their scientific objectives were specific: collect samples from the Fra Mauro Formation, an ancient geological layer believed to preserve records of the moon's violent early history. During 2 demanding moonwalks, they hauled equipment across broken terrain with a wheeled cart, covering ground in hours that would have taken days on Earth. What they brought back fundamentally altered lunar science. The rocks turned out to be impact breccias, fragments of material that had been shattered and fused together by enormous collisions billions of years ago. This was definitive evidence that the lunar highlands weren't the product of volcanic activity, as many researchers had assumed. They had been sculpted by a period of intense bombardment from space. And that discovery had implications far beyond the moon. If our nearest neighbor had been hammered that ferociously in its early life, Earth had almost certainly endured the same thing. I've been fascinated by this for years. It flipped planetary science on its head. And in a lighter moment near the end of the second moonwalk, Shepard pulled a makeshift 6-iron from a sample collection tool and drove 2 golf balls across the surface, sending them sailing in the low gravity. Even on the most dangerous frontier humans have ever explored, we remain fundamentally ourselves, but the mission that permanently elevated the Apollo program from a Cold War achievement to a scientific landmark was Apollo 15. Launched July 26, 1971, it was the first of the so-called J missions. Longer, more complex, more ambitious than anything that had come before. Commander David Scott and lunar module pilot James Irwin would spend nearly 3 full days on the surface, operating in a region called Hadley Apennine, a dramatic landscape of mountains, steep rills, and ancient valleys that looked unlike anything visited before. For the first time, a lunar roving vehicle accompanied the crew, an electric car purpose-built for the moon. Suddenly, instead of exploring a few 100 yards from the landing site, astronauts could range for miles, driving up crater rims and into terrain that would have been completely unreachable on foot. But the single most important find didn't require wheels to reach. Scott and Irwin spotted a pale, crystalline rock sitting in a small crater. Scientists later called it the Genesis Rock. At 4.1 billion years old, it is a piece of anorthosite, a mineral that crystallized from the Moon's original magma ocean as it cooled in the first moments of the solar system's history. Holding that sample was, in a very real sense, holding a piece of the beginning. Scott also staged an experiment that I think is one of the most elegant demonstrations in the history of science. He held a hammer in one hand and a falcon feather in the other, raised them to the same height, and released both simultaneously. In the airless vacuum of the Moon, they hit the surface at exactly the same instant, a live confirmation of a principle Galileo had argued for nearly 4 centuries earlier. Apollo 15's ALSEP instruments extended the scientific return even further, measuring seismic waves, heat flow from the interior, and the composition of the solar wind. The Moon had become a genuine laboratory. Apollo 16, launched April 16, 1972, pushed the inquiry in yet another direction. The target was the Descartes Highlands, a rugged plateau chosen because it was expected to hold some of the oldest accessible lunar crust. Commander John Young and Charles Duke were to land there, while Ken Mattingly orbited above. The same Mattingly who had been pulled from the Apollo 13 crew at the last moment over measles exposure, and who had watched helplessly as his crewmates fought for their lives. His time had finally come, and it almost ended before it started. A malfunction in the lunar module's backup attitude control system threatened to abort the entire landing. If the fault recurred on the surface, Young and Duke would have no way to lift off. Mission Control debated for hours, safety versus science, and the stakes were absolute. Eventually, the call was made to proceed. Young and Duke drove the rover across ridges and into craters, collecting samples from terrain that had been geologically frozen for billions of years. The chemical analysis of those rocks back on, Earth produced what might be the program's most profound scientific revelation. The Moon and Earth, it turns out, are chemical twins. The oxygen isotope ratios and trace element signatures in the Apollo 16 samples were nearly indistinguishable from those found in Earth's mantle. That extraordinary similarity provided the most compelling evidence yet for the giant impact hypothesis. The idea, first proposed in the 1970s, that a Mars-sized body called Theia struck the young Earth and the debris ejected into orbit coalesced into the Moon. The Moon's chemistry says Earth in every direction you look, but it's depleted in volatile elements and iron in exactly the way you'd expect from a world born in a catastrophic collision. The astronauts themselves noticed something unsettling. The dust that accumulated on their suits during the moonwalks carried a sharp, acrid smell, like gunpowder. Later research traced it to particles ground down by micrometeorite impacts and chemically altered by solar radiation. That dust remains, as of 2026, one of the most serious unsolved engineering challenges facing any future lunar presence. It infiltrates everything, abrading equipment and joints, and in sufficient quantities poses a genuine respiratory hazard. Our best engineers haven't cracked it yet. Which brings us to December 7th, 1972. A Saturn V rises from the Cape at 12:33 in the morning, the only nighttime launch in Apollo history. The sky over Florida lights up as though the sun has briefly returned. On board are Commander Gene Cernan, Command Module Pilot Ron Evans, and Harrison Schmitt, a professional geologist and the first trained scientist to reach the surface of another world. The destination is the Taurus Littrow Valley, selected for its dramatic contrast between dark volcanic plains and bright highland slopes, the kind of geological diversity that would tell multiple stories at once. Cernan and Schmitt would remain on the surface for 3 days, logging 75 hours outside the module, a record. They drove more than 20 miles in the rover and returned 243 pounds of samples, the largest haul of the entire program. Every stop was planned with the precision of a field geology survey, and it was Schmidt's trained eye that produced the mission's defining moment. Nears. One crater, he spotted something that stopped him cold, a patch of orange soil gleaming against the universal gray. Under his helmet light it glittered like embers. Back on Earth, the analysis revealed it to be volcanic glass. Tiny beads formed 3.6 billion years ago when fountains of lava erupted from deep within the moon's interior, cooled almost instantly in the vacuum, and rained back down as glass. It proved that the moon's volcanic history was far more dynamic and varied than anyone had imagined. The expanded ALSEP package deployed on Apollo 17 gathered data on seismic activity, thermal flow, and surface chemistry that painted the most complete picture of lunar structure ever assembled. Every core sample, every rock box, every instrument reading added another piece to the mosaic. On December 14th, as Cernan prepared to climb the ladder for the last time, he paused and looked back across the valley. His boot prints and Schmidt's would remain undisturbed for more than half a century. As of this writing in 2026, they are still there. Apollo 17 was the end of an era, but more than that, it was the era's highest point, the most scientifically productive mission of the entire sequence. Scientists continue to debate the finer details of lunar chronology to this day, and even the giant impact hypothesis has faced renewed scrutiny as the samples yield subtler contradictions. But here's what cannot be debated. In a parallel history where only Apollo 11 ever flew, we would have almost nothing to argue about. And I want to leave you with one final thought, one I find genuinely compelling. For anyone who has ever entertained the notion that the moon landings were staged, the later missions are actually the most powerful counter-argument imaginable. Faking one flight, conceivably possible in some fantastical scenario, but faking 6 across multiple years with a rotating cast of hundreds of engineers, scientists, and contractors, and then distributing hundreds of pounds of carefully catalogued rocks to research institutions across dozens of countries, rocks that have been analyzed, published, and independently verified ever since. The sheer volume of data produced by Apollos 12 through 17 is simply incompatible with fabrication. Every result has been cross-checked, replicated, and scrutinized by scientists who had no stake in NASA's reputation. Armstrong's step gave the world a symbol, but the missions that followed, the ones the history books barely mention, gave us the proof that it was all unambiguously real.